Okay, so now we are going to work through the problem that is essentially what you're doing for lab this week. Okay, we are going to have a cup of aluminum and we're going to fill it with water that's a little bit warm, and then we're going to add ice, and then we're going to see what should the final temperature be of our system. Okay, so we have an aluminum cup with water inside it, and they are sitting at room temperature and equilibrium. Okay, so the aluminum cup and the water initially are both at a temperature of 24 degrees Celsius. Okay, so we've got an aluminum cup with a mass of 70 kilograms. So the mass of the cup, sorry, 70 grams, 70 kilograms would be a big cup. An aluminum cup of mass 70 grams is filled with 200 grams of water. So that's going to be the mass of my water, 200 grams. And that water is also at 24 degrees Celsius. So the cup and the water have both achieved room temperature. Then we're going to take 20 grams of ice. That's the mass of my ice. And we're going to add that to the cup that's filled with water. And we're going to stir it up until everything melts, until all the ice melts. At that instant, at the instant when our ice finally melts, what is the equilibrium temperature of the water? So we're looking for the final temperature of our system. And we're going to assume that that ice cube that we added to the water was initially at 0 degrees Celsius, okay, right at the freezing melting point. Okay, so with all those bits of information, we're going to figure out what is the final temperature of our system. Okay, so in order to do that, we've got to think about the sum of all of the processes that lose energy and the sum of all of our processes that gain energy. And the sum of all of those has to equal 0. So we're conserving the energy lost in the system with the energy that's gained in the system. Okay, so let's break these up into their little bits. So we've got the heat required to cool the water. Okay, to get it from 24 degrees Celsius to some other temperature, to some cooler temperature. Okay, so in that way we're losing energy from the system because it's warm and it's going to get colder when we add the ice. And then we have to also cool the cup, this aluminum cup. So Q cup to cool the cup. Okay. Okay, so the cup is also losing energy in that process. And then we have the energy required to change the phase of that ice cube from ice to, from a solid to a liquid. And so I'm going to call that Q phase, to change our phase from ice to liquid. Okay. And then finally, we have the heat gained by that mass of ice as it warms from 0 degrees Celsius to our final temperature. So this is a heat gain. So this is to, well, what we'll call that? To warm ice. We're essentially warming the mass that was once ice up to our final equilibrium temperature, and that all has to equal 0. Okay. Using what we've learned in our previous questions for the pre-lab, this heat required to change the temperature of a substance is equal to the mass of that substance times the specific heat of that substance times its final temperature minus its initial temperature. Okay, plus we've got M of the cup times the specific heat of the aluminum that the cup is made of times T final minus T initial, plus this heat required to change the phase of our ice cube. So that will be the mass of our ice cube times the latent heat of fusion, okay, plus the mass of the ice times the specific heat of water times the final temperature of my equilibrium system minus the initial temperature of the ice cube, which we said was 0 degrees Celsius, because we're assuming that that ice cube is starting from 0 degrees Celsius. That all has to equal 0. Okay, so we have to solve this for T final. It's an algebra problem now. Now we've done the physics. Now it's algebra, okay? So we have to break this up, put all terms with T final on one side, all the other terms on the other, factor out a T final from one side, and then we'll get our equation, okay? So I'm gonna break this up into bits. So this term right here becomes MWCW T final minus MWCW T initial plus MC, is the cup, specific heat of the cup, T final, minus MC, specific heat of the cup, its initial temperature, plus the mass of the ice times the specific heat of water, because we're taking what was once ice and it's changed phase now, and then we're taking that water that's now 0 degrees Celsius to some further temperature, okay? And times T final, and that has to equal 0. Okay, so I've got, let's see, this term with TF, this term with TF, this term with TF. So I'm going to keep all of these terms with T final on the left side of my equation and put all of the terms that don't have T final in them on the right side of the equal sign, okay? So when I do that, I get MWCW T final plus MC, specific heat of my cup, T final, plus mass of the ice, specific heat of water, T final, that all equals. Now these terms, the remaining terms, I have to subtract to the other side. So that equals MWCW T initial plus MCCC T initial minus mass of the ice, latent heat of fusion. Okay. Now, from these terms right here, I can factor out a T final from the front. T final times MWCW plus MCCC plus MICW. That equals all the stuff over here, okay? So what I can do is I can divide both sides by this stuff right here that's in the parentheses, okay? And when I do that, I divide this side by all the stuff in the parentheses, I'm just left with T final. And if I divide this side by all the stuff in the parentheses, this looks like T final equals MWCW T initial plus MCCC T initial minus M initial latent heat of fusion, all divided by mass of the water, specific heat of the water, plus mass of the cup, specific heat of the cup, plus mass of the ice, specific heat of water. Oh my gosh, wow. Big equation. You're going to keep this equation handy in your back pocket because we are going to use it for the lab this week. Okay, now we have to plug in our quantities. And before I move on to plug in the quantities, okay, we need to write down what our specific heat of the water and specific heat of the cup, which is made up of aluminum. So we're going to use the specific heat of water of 1 calorie per gram degree Celsius. And we're going to use the specific heat of aluminum, which is what the cup is made of 0.22 calories per gram degree Celsius. And so what I'm going to do, since I've run out of room, is I'm going to erase this line right in here, and then we're going to plug in the numbers up here. Okay, so now we're going to plug in these quantities up here. So, you know, you've got to be really careful with which numbers you're plugging in where. You have to make a table so you can keep everything in line so you know what goes where. So this final temperature is going to be our mass of the water, 200 grams, times the specific heat of water, 1 calorie per gram degree Celsius, times the initial temperature of our system, 24 degrees Celsius, plus the mass of my cup, 70 grams, times the specific heat of the aluminum cup, which was 0.22 calories per gram degree Celsius, times the initial temperature, 24 degrees Celsius, minus the mass of my ice, 20 grams, times the latent heat of fusion. And I forgot to write down the equation for latent heat of fusion for water. It's 80 calories per gram. Okay, so latent heat of 20, so we've got the mass of my ice, 20 grams, times the latent heat of fusion of water, 80 calories per gram. And then we divide that all here by the mass of my water, 200 grams, times the specific heat of water, 1 calorie per gram degree Celsius, plus the mass of my cup, 70 grams, times the specific heat of aluminum, 0.22 calories per gram degree Celsius, plus the mass of my ice, which was 20 grams, times specific heat of water, which is 1 calorie per gram degree Celsius. Okay, so then this is equal to, this first term is 4,800 calories, plus the second term is 370 calories, plus my third term, actually this should be minus 1,600 calories, okay? And then we're dividing that all by 200 calories per degree Celsius, plus 15.4 calories per degree Celsius, plus here we've got 20 calories per degree Celsius. Okay, plugging all that in, we find that the final temperature should be 15.2 degrees Celsius. All right, so we take all these knowns in here. We start with an initial temperature of 24 degrees Celsius for our whole system. Then we add a piece of ice, and after that ice has fully melted, then our entire system should have reached a temperature of 15.2 degrees Celsius, and you could check it by putting a thermometer into the cup of water, and then you'll be able to check to see how close did you get to your calculation with your actual experiment. So that's what we're going to do today, this week. It's going to be a lot of math to keep track of, okay? We've got this equation, math to keep track of, so you've got to make yourself a table with all of your knowns, and you've got to put all of those terms in and show your work so that we can see where you're making a mistake, where you went wrong, so that we can be sure that you get to the final correct answer, okay? It's always important to show your work. Keep a record of your work. It's easier for you to then go back and catch to see where did you make mistakes if you end up getting the incorrect answer.